Okay, welcome back to the next video. So here we're going to talk about the configuration files. So I've chosen robot2d. So this is a configuration file which just happens to have a lot of the different parameters we would be looking for, so it's easier to explain because there's more of these parameters in there. Feel free to look at all the examples. Hopefully they all have plenty of comments and are well described so that they can be easy to use. So the first thing that we need is the parameters. So we set the dimension size using these parameters dim_x, dim_u, dim_w. So here the dimension of the state space will be 2. There will be 2 inputs and there'll be 1 disturbance. Then we can define lower bounds, upper bounds, and the step size for these parameters using curly brackets and a list. So if there's 2 parameters, you can have 2 items. If there's 3, you'd have 3, etc. So first of all, we set the lower bounds. So we're saying that both dimension 1 and dimension 2 are -10 as the lower bound. Then we can set the upper bound. We say both of them are 10. And then we can set the step size, or the discretization value. In this case is 1/2. We can do the same thing for the inputs, and we can do the same thing for the disturbances. In this case study, the noise we're considering is a diagonal covariance matrix, and so we can write this as a list. So here we have the different standard deviations which will be included inside, and this can be passed in to our normal noise distribution. The next 2 steps that we take are we write a logical expression for the target region and the avoid region. So these are done quite easily. We basically create this Boolean. What will happen is that by default the state space will be created. All of the states inside of the state space are described, and we will iterate over all of those states against these expressions. Any state where the expression is true will be removed and will be considered now a target condition or an avoid condition, or a target state or an avoid state. So here the target state is described as being somewhere in the first dimension between 5 and 8, and somewhere in the second dimension also being between 5 and 8. But again, like I said, this expression could be as complicated or as convoluted as you wish it to be. In the same way for the avoid condition, we say that between -1.5 and 1.5 in both dimensions, those states will be considered avoid states. The next thing we want to do is we want to describe the dynamics. So we have a 2D system, so we have 2D dynamics. You can see the state parameters x0, x1 are included here, and the input parameters u0 is used and u1 is used, and then also this disturbance term on the end. Note this disturbance is not the same as the noise. The noise is considered to be additive and it's considered on top of this, but this disturbance would be more like an adversary rather than as noise. Also note that these 3 parameters that we include, if any of these terms are 0, so for example if there's no input or if there's no disturbance, then we simply omit that from the dynamics. And this is important to do because otherwise it might throw an error thinking that you're using a disturbance when you're not. Let's now look at the main function. So the first thing we do is we create this IMDP object. We give it a name. In this case the name is MDP, and we give it several parameters. So we give it the dimension of the state space, the dimension of the input space, and the dimension of the disturbance space. We can then set those spaces more specifically using the lower bound, the upper bound, and the step size. And we can then also describe and find these target spaces and avoid spaces by relabeling those states inside of the system. Once we're happy with this, if we wish, we can save all of these to a file so that then we can analyze them, look at them in our own way. These will be saved into files ss.h5, is.h5, ws.h5, ts.h5, and as.h5, respectively. We then pass the dynamics into the system. So this again is just that function we wrote before. This will be passed into the object. We describe the noise type. So we have here normal noise. We could also have custom distribution. And then we also set the standard deviation. In this case, yeah, this sigma that we described before. For other examples of multivariate noise, there are examples, so do look at that as to how specifically to write the noise description in those cases. The next thing that happens then is the abstraction step. So here in general, there are always going to be commands mdp.min target transition vector or max target transition vector to create the abstraction of that vector. Because of the nice property that if the upper bound is 0, we can guarantee the lower bound is 0, we can reduce a lot of computations by using another function, target transition vector bounds, which computes both of these at the same time. When it's doing this, it will first compute the maximum bound, and then if the value is 0, it will automatically set the minimum bound to also be 0. And this can just save us some optimization runs, which for some of these very, very large matrices can be hugely time-saving. Again, if we wish, we can then save these vectors into a file, and we can do the same thing for the avoid regions. So an important property for the avoid regions is that it is very unlikely that the state space you're using is bounded in terms of the transitions will always remain within the state space. So for example, imagine a car traveling around some area. If you're on the edge of the area, there's probably a good chance that the noise would say that the next step would jump outside of that region. For the purposes of the tool, we consider everything outside of the state space that's been described as somewhere we wish to avoid. And so for this reason, even if you've not described this avoid condition, outside of the state space will still be considered an avoid region. And so you will always want to be having these two vectors, avoid transition vector, min and max, at all times. So that's an important thing to try and remember. And then finally, the last of the abstractions we do is we calculate the transition matrix between states inside the state space that are not either states to the avoid region or states to the target region. And these, once again, can be saved. The final step then is to do the synthesis. So this can be done over an infinite horizon using infinite horizon reach controller, for example, or it can be done over a finite horizon using the equivalent finite horizon. We consider three types of specification: safety, reachability, and reach and avoid. The code will automatically detect if you are doing a reach avoid specification or if you're just doing a reach specification. And so these are combined together using just the term reach. For a safe specification, we simply replace reach with safe. The value true here refers to whether or not we are considering the controller we designed to be pessimistic or optimistic. By pessimistic, I mean that we consider the worst case scenarios at all times, and so the input is based on the worst case scenario occurring. The optimistic controller is based on the best case scenario occurring. And both of these bounds will be determined, but it's up to the user to decide whether they wish to design the input based on the worst case scenario or based on the best case scenario. In addition, there is a nice algorithm that can do this all in the same way using a sorting method, which often provides quite decent speed-ups compared with the previous approach of solving a linear program. And so this one is also recommended to use. This algorithm is also very important for GPU considerations. So the sorted approach doesn't include any external libraries, and so it's the only method that's possible to be used by any synthesis using a GPU. Again, I have an example which shows the GPU inside of the code, so do look at that. But the important thing to note basically is that you cannot do any abstraction in the same file that you wish to do the computations using GPU, because the external libraries used in the abstraction will cause errors and will throw exceptions because the GPU parallelization cannot use the external functions that are used by some of those. Finally, at the end, you can save the controller, and you can use this in other applications. You can use it in Python, R, MATLAB, all of these different examples. I provided some code which can show you how you can open this controller and use it in MATLAB and Python and R. So do have a look at that. I believe it's in the miscellaneous folder. But yeah, thanks for giving me your attention, and I'll see you in the next video.